to the quicksort unit. In this unit, we're going to try to understand the intuition behind the quicksort algorithm and apply it to an example. We have to first understand that quicksort algorithm applies the divide and conquer strategy. What we mean by that is that we take the bigger problem at hand, which in this case is sorting a given array, and break it into smaller sub-problems of the same type, try to solve the smaller sub-problems, and then combine it to find an answer to the bigger problem. Let me explain this a little. So the intuition here in quicksort is that we try to take a pivot element. Now this pivot element can be any element in the array. We can choose to always take the first element, always take the last element, or always take a random element, or do some pre-computation and take a medial element, for example. Suppose in this case I am always taking the first element into consideration and making it the pivot. So if this is my given array, I take the first element here and decide that this is my pivot. Now what I'm going to try to do is kind of pseudo sort this array around my pivot. What I mean by pseudo sorting here is that I place my pivot in the middle and I try to place all the elements in the array which are smaller than the pivot towards the left of this pivot, and all the elements which are greater than this pivot towards the right of this pivot. What I will have when I do this is that I'll have my pivotal element here, and all the elements towards the left of the pivot will be smaller than it, and all the elements towards the right of the pivot will be greater than it, although these two sub-arrays might not be sorted individually. Now we can see what we need to do next. We need to recur on the left and the right sub-arrays with respect to this pivot, and we need to keep doing this till we reach a trivial case or a minimal case where, say, I have only one or two elements left in my sub-array. Let's try to apply this to a real-life example to get more clarity on this. Suppose my example is this array right here, and I choose the first element to be my pivot. So when 7 is my pivot, I try to place 7 in the middle and pseudo sort this array in terms of 7. So 6 is smaller, 8 is greater, 5 is smaller, 2 is again smaller, 9 is greater than 7, and 1 is smaller than 7. So here at this stage we can see that my pivot is 7, everything that's on the right is greater than 7, everything that's on the left is smaller than 7. However, this array in itself and this may not be sorted. In this case, the right part is kind of sorted, but the left part is not. So now I have recurred, this is the first part. Now I want to recur on this left sub-array to do the same thing. In this case, I choose my first element, which is 6, to be the pivot. Now since 6 is my pivot, I will try to pseudo sort this array around 6. 5 is smaller than 6, 2 is smaller than 6, 1 is also smaller than 6. So I have reached a trivial case here where there is nothing on the right sub-array, so I can stop this level of recursion right here. Okay, now let's look at this case. Suppose here I change my policy and I try to say that, say 2 is my pivot element here. When you're trying to follow one policy, you should always follow it, but just for an example, let's say I'm choosing random pivots now. So 2 is my pivot right here. If 2 is my pivot right here, then I will try to sort this array with respect to 2. I'll get 1 here, which is smaller than 2, and 5 and 6, which are greater than 2. Now again, when I try to recur with this sub-array, it has only one element, so it's sorted by itself, and here I have two elements, so I can recur to the next stage and sort this, get 5 and 6. Let's look at what's happening in the other subtree. Here we had 8 and 9. So suppose I have recurred and I have chosen 8 as my pivot. Then I have 8 here and 9 goes towards the right of 8. So this is sorted. Then I try to recur on 9, which is one element in itself, so it's sorted by itself. At the end of this, when I try to combine my result, I will see that I have 7 was my first pivot element which I sorted. Then towards the right subtree, 8 was my next pivot element and 9 was my next, which is sorted here. On the left part of the subtree, we had chosen 6 as our pivot, which goes right here, and then we had chosen 2 and then 1. So this becomes 1, 2, 5, 6, 7, 8, 9, which is the sorted example. Let's try to also look at how exactly we do this pseudo sorting around a pivot element. Suppose my pivot element was 7 and I had some elements here and some elements here. In this case, I had chosen my pivot to be the first element of the array. So my original array would have been something like 7 followed by some values. What we try to do is keep an indicator here and keep another indicator towards the end. And we try to see if both of these values are in the correct places. Suppose if this number was 2 and this number was 8, then I know that 2 is supposed to be towards the left of 7 and 8 is supposed to be towards the right of 7. So this is fine, because in the end I would want to swap 7 with the medial number here, so that 7 comes in the middle, everything towards the left becomes smaller to it and everything towards the right becomes greater to it. But if I have a number like here I have a 9 and here I have a 1, then I know that these are not relatively correctly positioned. So what I would do is, if my indicator is here and here, I will swap these two elements to get something like 7, 2, 1 and here 9 and 8. The other number here was 3. So I have looked at these two, then I looked at these two. Then when I move my pointer and I reach here, I know that I've checked all my elements. So I will take this element and swap it with 7, so that I get something like 3, 2, 1, 7, 9 and 8, where 7 is my pivot, everything towards the left is smaller than 7 and everything towards the right is greater than 7. The complexity of doing this entire operation, because we are looking at each number in the element exactly once while iterating, is O of n.